Yeah, welcome, and thank you all for coming to my talk, and thank you very much for inviting me to Iran, for giving me the opportunity to give these lectures. I very much appreciate it, and I very much enjoy my stay here. And so my idea for this winter school was to give a series on lectures on computational geometry with bounded workspace. And so this is a relatively new and growing area within computational geometry, so it's not just one paper, but many papers have been written on this by now. And so the idea is to give you some idea what's happening in this area and to give you the basic model and some basic results, and then it can get as complicated as you want it to be. I mean, so I will start out simple, but you can also have more deep results in case you get bored, but we can also stick with the simple things. But for this lecture, what I wanted to do is I just wanted to tell you what exactly the model is. I wanted to give you some context about what you should think about this model, what was there already, what is new, what is different to things which have been done in the past. And then show you some 1, 2, 3, depending on how much time I have, basic examples, very simple things, to get some feeling of the model, what's possible, what kind of results are possible, and so on. Yes, so let me start. So again, computational geometry with bounded workspace. So let me briefly sketch the model and then give some motivation for why we might be interested in something like this. So let me explain the situation when you're looking at algorithms with bounded workspace in computational geometry. So what do we assume, or what's the mindset we're in when we're working on this? So first of all, the idea is that the data is big. So the input is big. Or let me say input instead of data. So the input is very big. So input is big. And it's somewhere in memory, so we assume we have the input given in some array maybe, some data structure, and so maybe that's the first part of the input, the second piece of the input, the third piece of the input, and so on, n pieces of the input. So it's just some items of the input. So this is our input, and we think of it being very big. So this is, I mean, it looks small on the board, but actually it's a lot, right? So the input is big, and so you think of it maybe as some huge storage, DVD or Blu-ray disc or something very big that you want to compute with. And the available memory that you have itself, so your RAM, the random access memory that you have in your computer, is small. It's very small compared to this. So this is the input, it is very big, and so here you have some very small memory in your computer. So this is the RAM. This is the input. And so what else do we assume, right? So we think that we can assume we can access the individual pieces of the input randomly. So you can say, oh, I want to have the third element of the input like this, and you get it immediately. Or you want to have the nth input of the input, you get it immediately, right? So it's so you have random access to the input. Random access. So like on a CD, DVD, or a flash drive. But we cannot change it. But are not allowed to change it. So we assume that we can have any piece of the input that we want as quickly as we want, but we are not allowed to change anything, so we are not allowed to write here. But we are allowed to write there. So we have this tiny piece of memory. We have our random access memory, our RAM, and our computer or our cache or whatever. And so we are allowed to write here and to do our computations here. But here we are only allowed to read. And the third thing is, so here, right, so we can read it and, of course, copy some stuff to the RAM and use it in our workspace, but more is not allowed. And finally, so we have some output device, but so this output is write only. So we can write something to some memory, but once it's written, we don't see it again. So it's maybe like a printer or a monitor. So you put something onto the screen, and then it's gone. But of course, then somebody else can come and read it and use the information for their benefit, but the algorithm is not allowed to use anything again what it's written. So the output is write only. Okay, so here we have some output. And so you can imagine it to be a printer or a screen or something, so it's gone out and cannot be used again. And so this is somehow the way we think of computation in this model. Right? So we have a big amount of data, it's there, we can access it, but we cannot change it. We have a small amount of workspace where we can read and write, and we need to output something. So we want to compute something from the input, we need to output it, but we are not allowed to read again what we output. Yes, so this is what we are looking at, and so maybe let's first, the first question you might have is why? Right, so why exactly this kind of model? So why do we have this big input that we cannot write? So why do I disallow write operations? Why can I not use the output again? And so on. So what is the motivation for this? Where does it come from? And let's see. So the motivation or the justification. So unlike David in his talk, who talked about some problem which has been very well studied since the dawn of computer science, maybe since, or maybe I'm not allowed to say, maybe since most of us were before we were born. But so this is something well justified. So I need to at least spend some time to motivate and explain why I do what I'm doing, because this is relatively non-standard. So let's see. So what is the motivation? Why? Okay, so the motivation is, so first of all, the idea is that nowadays there are many small devices and small sensors. So we have many small devices that are distributed, and they have something called flash memory. So yeah, so you all know what flash memory is. And so this flash memory, it's a kind of memory, so the technology implies that it's easy to read. So you can read very easily and quickly, but writing is a more cumbersome process. So it takes longer, and also when you write too often to flash memory, it can get damaged, or then it somehow doesn't work anymore. So you somehow want to restrict the amount of write operations. And so a radical solution for this is the idea that you don't want to overuse the writing capability of your memory. Is just to say, okay, I disallow it completely and see what I can do in this very restricted model. So this is one idea. So you have like small devices. These small devices, they don't have much memory, but they may have a large input because it's cheap to have some big read-only memory or some flash memory where you put the input once, but you don't want to write it too often. Then another reason would be concurrency. So we have this data, and it's in some big memory, but I'm not the only person who's using this data. Right? There's somebody else who wants to use this data, so there's some other algorithm or many algorithms, and they all want to work on this input, but they have different objectives, different reasons why they want to work on this input. And so now if my algorithm starts changing around things here in the input, that's very annoying for the other algorithms, because then they cannot really use it anymore. So then the idea would be, again, you want to have some, you don't want to change the input, but you have some relatively small memory, and you want to do your computation in this relatively small memory. Yes? So that's another justification. Then, of course, another reason might be safety concerns. So what do we mean by this? So the third possible motivation is that you say, so some of my RAM, so this belongs to me, nobody really sees what I do here, but then this large input is somehow more public, and so when I start writing here in this big memory, other people can see how my algorithm works, what it does, and I don't really want to reveal this information, and so it's better not to modify the input. Yes, so that's another possible motivation. And of course, the third one, since we're all theoreticians, I mean, that's an interesting theoretical model, which actually has already been studied before in the context of complexity theory, just to see how much can you do when you restrict your computational resources, or how much is possible with bounded amount of resources. So what can you still achieve when you restrict the amount of workspace, and how essential is the workspace for efficiency, or is it actually not essential? Can you solve the problem still efficiently without really using memory, but maybe by investing a little bit more time, but then how much more time do you need, and so on. So these are all interesting questions from a theoretical point of view, and since I'm talking to a theoretical audience, maybe you may also be intrigued by these kind of questions. So of course, then the fourth motivation is the theoretical interest of the model, in the sense that it gives us some insight into the nature of computation, right? So what do resources mean, and what kind of influence do they have on the efficiency of our algorithms? So yeah, so far for the motivation, and so then also let's see. Or do you have any questions so far? Do you buy the motivation? Yeah, you have a question?
What you can allow some writing and still do those applications.
You're right. Yes. I mean, this is one possible model. So these are the motivations, and then from these motivations, I extract some theoretical model. And so my, I guess. The justification why I say that I completely disallow these write operations is, I would say, from a theoretical viewpoint, it's the simplest model. But you're perfectly right. You could say, so from these motivations, I take the conclusion that I say, okay, writing is maybe not desirable, but not fatal, right? So I don't want to completely forbid it. I just want to restrict it. And then you can somehow define another model where you count the number of write operations. So you put some restrictions on the allowed write operations, and you see what happens then. That's a perfectly reasonable thing to do. And I'm sure you can also get interesting results there. And actually, so I will talk about related moments just in 1 minute, and I say that talk about how people have worked on this also. So my reply why I'm looking at this would be, so this is just a radical and clean way of addressing the problem. And it's somehow the first way of addressing the problem. So you say writing is bad, so I just completely forbid it. And then I see what happens. And then once I understand what happens, I take the next step, and then I say, okay, now I have some understanding what happens when writing is disallowed, and now I see I'm allowed to write a little. And so in this context, then I start to, building on the insights that I had from the read-only model, I would try to find out what happens then and to extend it. Yes, so this is perfectly good and intelligent research direction, I would say. Yes. Any more questions about the model or the motivation? So since I'll be talking about this for the next 4 lectures, so I thought it would be good to go into some details. Yes?
Is the input dynamic? I mean, there's no guarantee that a sensor can return the same data from time to time.
No, so the input it's fixed. So you really think of, so it won't change. No, so this I assume that it won't change. It's fixed, but it would also be interesting to say maybe the input evolves over time slowly, and you want to adapt your algorithm or your data structure. That would also be interesting to look at. But so far, I'm not considering this. Yes?
Compared to external memory models, here reading input is expensive or no?
It's not expensive, but I will talk about this right now. So I wanted to speak about related models. So you're leading up to the next part of my talk. Thank you. So now that we have the motivation, the next question. So the first question you had is why, right? So and I hope I gave you some answers of why might be interesting. So why this might be interesting. The next question is, hasn't this been done before? Right, so why now? Or why, or what has been done already? And so this is the next question. And so, yes, of course, I mean, theoretical computer science has been around for a long, long time. And, well, 40 years, or 50, 60, depending on how long, well, 80 years if you're generous, or 2,000 years. So for a long, long time. So hasn't this been done before? And so so my answer to this would be similar things have been done before, but not exactly what I'm talking about right now. And so let me see what these similar things are and how they relate to what has been, what I'm doing here. So let's speak about related models. So what do we have here? So there are many, many models. So theoreticians like to come up with models. And so I counted 1, 2, 3, 4, 5, 6 models that are somewhat related. So let's see. So what do we have? So the first model that you might know is streaming. So there's the first model is the streaming model. And so there's a whole subfield, and it's pretty big. So it started something like 20 years ago in theoretical computer science, which looks at streaming algorithms. And what is the difference, the similarity between my model and the streaming model? So the streaming model says, so it's similar. So the assumption is the data is very big, my memory is very small, and I want to process something on the data. But now the difference is that I'm not allowed to access individual elements of my input as I choose. So in streaming, I have to read my input from left to right. Yes, so in streaming, the model is I do not have random access, but I have to read my input from left to right, and I'm supposed to compute something on this input, and I'm allowed to remember some stuff, but the amount of things that I'm allowed to remember is much smaller than the potential input that I have. Yeah, so it's similar in the sense that the input is read-only and that I only have small memory, but it's different in the sense that I'm not allowed random access to my memory, to my input, but only left to right. So streaming, it's left or maybe right to left. So do you read the input from right to left or from left to right? I mean in one direction, yes, so you understand. I mean you can translate, I'm sorry. This is my cultural bias. So input can be read only in one direction. And so that's the streaming model. And there's been a lot of work in the streaming model. So many variants of the streaming model, a lot of work, a lot of interesting results. But it's different from what I'm doing. Then something, a variant of streaming which is interesting for us, it's multipath streaming. Multipath streaming. And multipath streaming, as the name suggests, so it's similar to streaming that you're just allowed to sweep over your input, but in streaming you're just allowed to go over your input once. And in multipath streaming you're allowed to read the input several times, but a bounded number of times, so it's a controlled number of times. You cannot just say, oh, I want to have the first element, and I want to have the 20th element, and I want to have the 5th element, and so on. But you have to read all the elements in order several times, and you don't want to do it too often, but just a bounded number of times, and so this always costs you something to do this. Yes. So this is the second model, or the variant of the streaming. Then, as you already mentioned, there's external memory algorithms. And external memory, or just external algorithms, so again, we have the assumption that our input lies in some very big memory, which I cannot really access at will, and which I cannot, and that I have some small RAM which is fast. But in the external memory model, I'm allowed to change my input, so it's okay to write into the input, but writing is expensive. So in external memory, the measure of performance for my algorithm is the number of read-write operations I do to this input, and I don't really access the input individually, but I subdivide the input into blocks, and the blocks, they consist of many elements from the input, and the measure of performance for my algorithm is how many blocks do I need to read and write in order to achieve my goal. And so this is external memory algorithms. And this is again very similar to, I mean, in some sense the motivation is similar, but then the concrete model is different because on the one hand I'm counting something else, and on the other hand I'm really allowed to change my input. So this is external. So these are the two differences. But the kind of motivation comes is similar, but the viewpoint is more from a database viewpoint, and it's also, let's say, more, it's more focused on big machines, whereas our model is somehow more focused on small machines. So somehow the thinking, Okay, then the third model is something called in-place algorithms. And so in place means, so sometimes it's also by people who want to be fancy, they call it in situ in the Latin. So it's the same thing. So in place means, so it's again a similar model. So you say you have a big input, you have a small working space, but now you're allowed to change the input. But you're not allowed to use any significant amount of memory in addition to the input. So you're allowed to write in the input, you're allowed to move it around, but you're not allowed to use anything additional. So you're just allowed to use the memory that is used to store the input. And if you change it, then you might lose some information in your input. So I can write something here, but then I forget what X3 is, unless I remember it somehow or put it somewhere else. So this is in-place algorithms. So in this model, and okay, I mean, in addition to this, I'm allowed to use a constant number of variables. And then the game becomes, so I have some data structures, I want to build a tree maybe on these things, but I'm not really allowed to store a tree, because if I want to create nodes or something for my tree, then I start, I have to allocate memory for the pointers and so on, and then when I allocate the memory for the pointers, I would have to overwrite some of the stuff here, and so it's a problem, and then I start trying to encode these pointers by shuffling around the input and so on. So it's a fun model, but also different from what I'm talking about here. And maybe another model that's related, which also relates to one of the questions that came up, is called, and this is relative. So let's say, so these two models, they are pretty big. So there's a lot of work on these. So there are many papers on external memory, and there's a lot of papers on streaming. So in-place algorithms is a bit smaller. So I think there's been some work on this maybe 5 years ago, and then it got a little bit more, I don't know, it seems to have been less active in the last few years. And then the final model that I'm mentioning, it's relatively new, so I've only seen a few papers on it, but it's also interesting. But I have to say I haven't really thought about it, except that I know that it exists. And this model is called where leveling. And so what does this mean? Again, the motivation, it comes from flash memory. And this observation, or this phenomenon that people have observed, is that writing on flash memory is bad. And in particular, if there's a certain location in the memory where you write a lot, so this is bad for this location, it damages it, right? So, and so what you want to do is you want to have an algorithm which is somehow very democratic about how it uses its memory size, right? So it doesn't, there shouldn't be like one very important piece in memory where you always write, like the root of your search tree, where you always read and write and change a lot. So, and then this location will be damaged when you do this, but so you want to design your algorithm in a way such that it moves the data around and reads and writes, in particular writes, into the memory very evenly as possible. And this is the so-called where leveling model, and there's been some work on how you design data structures like hash tables or search trees in such a way that the memory the flash memory is not damaged, right? And so it's also interesting, but there hasn't been too much work on this yet, as far as I know. Okay, so this is the related models, and maybe let me mention one more. I mean, there's also one model which is not so related, not so very similar, but it has some similar flavor, and this is called succinct data structures. And here the idea is, in succinct data structures, you really want to minimize the number of bits that you're using. So this is also the idea is memory is scarce. You want to store something, you want to store some data structure. And in succinct data structures, the idea is that you want to minimize, so you really count bits, right? So you don't say, oh, I want to store n elements of data, so O of n pieces of memory is okay for me, but you say, oh, I want to store a set of n elements, and information theory tells me that in order to store a set of n elements, I need n log n bits, and I want to have exactly n log n bits, and not 2n log n. That would be very bad. So this is succinct data structures. It's not, I mean, it's not very related to the model that I'm talking about, but it also has this kind of memory, like trying to be efficient with memory flavor about it. Yes, so and these are somehow the related models so that you see how, what the context is and how our model fits in to the work that's been done already. I'm sure there are other models which I forgot, but so at least you can, I hope you can appreciate that there's been a lot of work on this, and also that somehow nothing really exactly like what we've done has been done before. Well, I mean, it's not really true. I will talk about it a little bit later, but so it's somehow a gap in what we're looking at. So everything clear so far? It's, yeah, it's all philosophical so far, right? So it's no, yeah, but okay, so this is the context, and now let's get a bit more technical because so let's get back to our model, right? Back to our model. Okay, so now I gave some motivation and I gave some similar models that are known before, and now let's get back to our model. And so now we really want to work in this model. And so in order to work, I think I should really tell you what exactly I mean when I'm talking about the model so that we really know what we're talking about. So because I just gave some vague intuition, and so I think everybody hopefully got some idea of what I want to do. But still there's some ambiguities there, right? And so maybe we should first clear this up. And so is there something which was not clear in what I said? So is there's some things that are somehow vague, left vague. No, or you're completely, you have a question? Yes, what's vague?
What's the goal of your model? You want to minimize the time of the algorithm?
Yes, exactly. So, so what are the parameters that I'm looking at? How do I measure efficiently? So that's why efficiency, yes. Right, so yes, so I will address this. So the brief answer is, so there's several versions of my model. And so first of all, there's the model where you're just allowed to use a constant number of additional words of memory. And then the goal is that you want to be as fast as possible, right? So as usual, when you try to design algorithms, the first goal is always the algorithm should be as fast as possible. And this is our goal, the first goal. And then the second goal is, so now that when we understand what happens if you're just allowed to use a constant amount of memory, you say I gradually increase the amount of memory. So typically when you want to solve a problem in this model, it's been solved quite satisfactorily in the case that you can use arbitrary amount of memory, usually linear, for most of the problems that I mentioned. And now hopefully we're at some point will be, for some problems, at least also that's my intention for this series, we will understand what happens when we have a linear amount of memory, we will understand what happens when we have a constant amount of memory, and then the next question would be what happens in between. So you say you give me some number s of memory, and then the goal would be to be as fast as possible using s memory, and you want to have some situation where if you have a constant amount of memory, your algorithm is slow, maybe, well, okay, but not so super. Then you have n amount of memory where the algorithm is as good as it can get from what we know, and then you want something in between which gradually improves as you increase the amount of memory, and then you want to understand what kind of trade-offs are possible. So how much memory do you need to be good, and how does the transition occur? Yes. So this is one question. So what exactly are the parameters of the model? And the other model is, the other question that's left vague is, so what exactly do I mean by memory? So, and more precisely, so what do I mean is a cell of memory? So, so somehow I said the input, it resides in n cells, right? So here I wrote this x1, x2, x3 up to xn, and then I said this RAM is relatively small. Let's say it's like O of 1 cells of memory. And so what exactly do I mean? So a constant number of cells. And so what exactly do I mean by a cell? And to be honest, so if you try to read some papers on this model, it turns out that people don't really say, or sometimes they say, but it's a bit vague. So what exactly do we mean by a cell of memory? And there's two possible answers to this, two possibilities. So actually, it's not clear. You can decide what you mean by a cell of memory. So two answers. And so one answer, the easy one, is so you say, okay, so if the input size is n, right? So there's something, the input size, so we don't really know what the input size is, but so let's say, so it depends on the problem what exactly n is, right? But so the input size is n, then one cell of memory is a word of log n bits, O of log n bits. Then one cell equals O of log n bits. That's one answer, right? And then I can do operations on these cells in constant time as I please, can do the usual computations on it. But so one cell equals log n bits. So actually, I'm speaking about constant workspace, but so if you measure it in bit, it's not a constant, but it's actually log space. And so the cells, they can be, and then you can decide whether you allow that you actually meddle with the individual bits of these words, or you consider them to be atomic. But so the idea is log n, and so do you know why log n is reasonable? So why log n? Why not less? So why don't they say like 1 bit? So why do I need at least log n bits? Do you have some idea why log n is somehow the reasonable thing?
To store your numbers.
Exactly. So first of all, there are several answers. So the first answer is that I want to. I have n things in my input, and so somehow I want to be able to have n different things, right? For the problem size reasonably to be n, I somehow want to be able to represent n different things, and so I need n log n bits. And maybe I want to have the problem interesting, so I want to have significantly more than n bits, and so then I want O of log n bits, and so this means I can at least have some polynomial in n different things in my input. So that's the one answer. So if it's much less than log n, the problems are not interesting because the input space is not interesting anymore. And the second reason why you want log n is also here in this in your workspace you want to be able to store a pointer, right? So you somehow you just have some constant number of cells in your workspace, say, or a bounded number, but still in these cells you want to be able to somehow say some interesting information that I'm working on is stored in cell number 50 or something like this. And in order to store this, of course you need log n bits, because otherwise you cannot address, you cannot really address this amount of memory cells, right? So this is the reason why log n is a reasonable bound. So much less than log n doesn't make sense, and so somehow log n is the first threshold where it becomes interesting. Yes? So, so why is this? Okay, so why is this good? So why would you do like this? So what's the advantage of defining a cell like this? So so there's some advantages and some disadvantages of doing it like this. So the advantage is, so one of them is, so it's very clear what is happening. So it's clear. And easy to understand. And also another advantage is, so I said now it's a log space, and so So this model, if I define it like this, then it's actually a very well-known model, because if I define it like this, it matches the complexity class log space. And so if you do complexity theory, there's different complexity classes. I'm sure everybody has heard about P and NP, which are classes which concern deterministic and non-deterministic time, but there's also complexity classes which concern space. And so one complexity class, the smallest complexity class that concerns space, is called log space. And this is exactly my model if I define a cell to be log n bits. And so for this model, there are actually some known results, few algorithmic results, but quite a lot complexity theoretic results. And so here then I can go and read the papers from complexity theory and try to see what kind of tricks they use and try to use them for my problems. So it corresponds to log space. The complexity class log space are also called L. But the disadvantage when I do it like this is that this model, it can be restrictive. So and by this I mean that if I say my inputs they consist of log n bits, then in the context of computational geometry, it's somehow strange because it means that that the points I have, they lie on a grid and they have bounded precision. And so some of the assumptions that I make about my input are stronger than I usually do when I do computational geometry, right? And so it may be that I'm saying an algorithm is optimal, but actually in this model the algorithm is not optimal because I can do additional tricks which wouldn't be allowed usually in computational geometry. So it may be a bit restrictive and really not in the way we think about computational geometric problems. So also you have log n bits, so how would you compute distances? Can you represent even a circle or points on a circle properly? And all these things, right? So that's somehow annoying. So it's restrictive. So that's the one model, the one way. And so this would somehow correspond to something, if you have called it, it's called the word RAM. Okay. And yes?
You said that one answer is the size of cell of memory is related to our input size.
Yes.
It's not obvious for me because we have constraint on size of memory.
Yes.
In this problem.
Yes.
So if our input size increase, our memory size will increase too.
Yes. Okay. Yes. Okay. So you're criticizing the fact that here I use log n bits, and the number of bits that corresponds to the number of the input. Yes. Okay. So my answer to this is the answer, basically the same answer I gave before, that that you have to. So somewhere there has to be log n, because otherwise you cannot do anything. So I'm saying that if the size is less than log n, it somehow doesn't really make sense, or I cannot really, or the whole idea or the whole subject, it becomes different if I want to have some real constant here, because if I only have a constant number of bits, then I only have a constant number of problems that I can solve, more or less. Right? So I mean, you have inputs, and the inputs, they are all 5 bits numbers. Right, so then you can have, okay, I mean, you can still have inputs with n 5-bit numbers, but in these n 5-bit numbers, all of the numbers will be the same. Or I mean, you only have, you give me 1 trillion 5-bit numbers, then most of these 5-bit numbers will be 10 or something like this, and then it's not really clear that there will be interesting algorithmic problems for these kind of inputs. So at least, I mean, the algorithmic problems would be very different from the ones that we're used to studying. So that's the reason why I want to have something which grows with the input size, so that if I have n different things in my input, I really want to be able to encode them reasonably. And also I want to be able to address the memory such that, right, so I want to be able to store pointers, because if I don't really have the possibility, I mean, I have n things in my input and I somehow have to be able to do random access, right? So that's what my model said. I have n things in my input, and I want to be able to access elements in my input at will. And so I need to have log n bits somewhere in order to indicate my hard drive or whatever, so the thing that accesses the memory, which cell of the input, if the memory I want to access, right? So I need to have these log n bits, otherwise I cannot tell my hardware which part of the memory it should read. And then I can only access a constant number of memory cells, and then the problem is not interesting. Right, so then I would be in the streaming models. Then I mean I would have to define a different model which allows me to read the input, and then maybe streaming would be one reasonable answer. Yes. So another, yes?
It seems that you have another, let's say, hidden assumption.
Yes.
That the number of inputs are much more than the bits of each cell.
Yes.
I mean, if it is not true, then the size of your memory must not be log n, let's say. I mean, if each cell needs n bits and the number of inputs are log n,
yes.
So one cell of your memory must be n.
Yes.
Size of n, or n, not log n.
Yes. So you're saying, I'm not sure I completely understand. So you're saying that, what I'm always assuming is that I have a lot of different problems that I need to solve. I mean, the number of possible inputs is very big, and and so my algorithms, they need to work for all these inputs. So I cannot really cheat by somehow assuming that there's only few inputs and I specialize to this.
I mean, you said that your memory each must be at least of log n.
Yes, beta of log n. Yeah.
What if your bits of each cell be, let's say, n?
Yes.
And the total number of input is log n.
Yes.
So for saving each cell, you have to have at least O of n memories.
But so my total number of inputs is log n. Yes. And so for each cell I had, yes. So then I would be cheating, right? So that's why log n is also, I mean, if I have too many bits and I allow to access the bits individually, then I would somehow be cheating, because so if I make these cells too big, then I would have too much memory, and I would be lying to you if I say I only have a constant number of cells.
I mean, maybe
yes.
It's better that you say the size of our memory is the size of one cell.
Yes.
Not especially bounded it with O of log n.
Yes, so you can, okay, so it's proportional to the size of one cell. Yeah, okay, yes, that would be reasonable, yes. You can do this, yes. Okay, so this is the one possibility how we can do this. Okay, or are there more questions about this? So, I mean, this is right, it's important because I'm going to talk about it. So we will talk in this model, and so it will be important to understand. So the other, so this is A, and now, yeah, so let me talk about B. So the other way is, so B corresponds to the real RAM model that you may know from computational geometry. So I'm saying now that every cell, each cell stores a real number or an integer. And these are atomic. And so, yeah, so this gets a bit vague. So now somehow my cell, so what does it, it's very strange, right? So now I'm somehow allowing that every cell can store an infinite amount of information, like a real number, or so, which has infinite precision, or an integer. But I'm saying that these things are atomic. So I can just, I cannot really fiddle with the individual bits or anything, but I can just modify these numbers by using addition or multiplication or subtraction, or even now I can allow square root because I have infinite precision, or sine, cosine. So now I'm in a model which is more friendly for me because it allows the computational geometry operations. So we can do things which we want to do in computational geometry, like decide whether a point is on a circle, generate points on a circle, have these kind of things. But now I need to be somewhat careful how I may use this precision. I'm only allowed to use it in a benign way, so I'm allowed to use some kind of multiplication and division and sine cosine things on this, but I'm not really allowed to cheat. And the bad thing is, if I'm not careful, I can cheat, but somehow this model is easier to think about and to design algorithms and then to implement it. So yes. So we have integers and we have arbitrary precision, but these integers are atomic, so I'm only allowed to access them in a well-defined way. And so when I look at an algorithm in this model, I somehow need to be careful that it does not cheat. And so the particular source of cheating is the floor function. So I'm not really allowed to compute the floor of a real number, so to round. Because it has been shown that if I'm allowed to round and I'm allowed to compute with arbitrary real numbers, then I can do very crazy things. So this I forbid. And so here we need to be. So this model is somehow nicer from a theoretical point of view, but we're allowed to. But then it can happen very easily that we do things which are, from an algorithmic point of view, somehow unrealistic and not nice. Yes. But the good news is so now I talked for a long time about the model, and so at least let me put in like 1 or 2 examples before we stop. I think I have maybe like 7 more minutes or something like this, right? But so the good news is somehow the model doesn't really matter, right? I mean, it's good to have talked about it once so that we understand what the problems are, and that actually when we read papers and we want to evaluate the claims of people who write these papers, that we really understand what kind of the underlying assumptions they make and what the pitfalls are. But on the other hand, for the everyday work, you don't really have to think about too much what the model is, so you know what's allowed and what is not allowed. And someone need to make sure that the algorithm only does reasonable things. And so then you look at the algorithm and then you can see that it only does reasonable things and you're satisfied, but you should be aware that when people claim like great results, it may be that they're just somehow cheating with the model. Okay. Yes. Okay. So far about the model and the philosophical part, and now that we understand this, so we can maybe look at one very simple problem, and so let's see what the solution is. I mean, really simple. And then in the next lecture, I will look at some other problems from computational geometry that you know, and see how we can solve it in this model, and so it can get increasingly more complicated. So let's solve the first problem. And so what is the first problem that you solve in computational geometry? So if you've done so whenever you define a new model in computational geometry, you have to solve one problem. What's the problem? Convex highs, of course. Yes, thank you. Convex highs. So let's look at convex highs. Okay, and so now I defined my new model, and so now we have the standard problem in computational geometry, convex highs, right? So everybody knows what the convex high problem is. So you're given a set of points like this in the plane, and you want to compute the convex high, which is that thing, right? And everybody knows what the convex hull is, or should I write the definition or say something more? No? Everybody knows. Okay, so everybody knows what the convex hull is. Everybody knows how to compute it. Yes, so what algorithms? What's the Graham scan? Okay, so you know, so what do you know? You know Graham scan. What else do you know? Divide and conquer, yes. And one more? Gift wrapping. Gift wrapping, yes. And now I defined my new model. And maybe before trying to come up with new algorithms, maybe the first idea would be to think about, so always the first step, so we are in this new model and we want to solve something. We want to solve problems which have already been solved under different assumptions. The first step is always to try to understand what kind of solutions are already there, what kind of ideas are there in these solutions, and how can I use these ideas now for my new setting. Right now I have a problem, this problem has been solved, but so the problem has not changed, but I have changed, my mindset has changed, now I care about different things, and now I look at the problem again and the solutions that I know again from a new viewpoint, and I want to see what does my new viewpoint, what kind of insights does it give me to the solutions I know already. And so this is exactly what we can do now, right? So now here we have three algorithms. We have this new viewpoint, and we want to see, do these algorithms give us anything interesting for a new viewpoint, or is it just completely useless and I have to start again? Right? And so let's see. I guess I was a bit biased in the order. So do you know how Graham scan works? So so everybody knows, I guess. So you go from, you sweep over the input, you have a stack. You always, and the stack, it contains the convex hull of the points to the left, to all the points that you process already. Then you take the next point and you remove all these points that are somehow invalidated by the next point from your stack, and you add this point and you update the convex hull. Right? This is Graham scan. Right? So everybody knows it enough to understand what I just said. Or should I draw a picture? Yes. Okay. You're bored. Okay. And so now from the constant workspace perspective, so is this algorithm, does it work in my model or does it not work? And why or why not?
First you should solve it.
Oh yeah, you have to sort first. Okay, but okay, so you can. Okay, so this is the first problem. That's a good point. So you have to sort it, but okay, so I can solve this problem, right? So I can, because I can always remember the last point that I looked at, and then I can find the next one easily. So maybe it takes a bit longer, but I can do it. It takes more time, but still. Okay, so you found the first problem, but so this bug I fixed. Okay, so still good. So is there another problem that you might have?
The convex hull has all n points, so we need a stack n.
Exactly.
But can we store all n points? No.
Yes, exactly. So the more significant problem that I don't know how to fix is that you need to have the stack, right? So you have this dynamic convex hull which evolves over time, and you store it in a big data structure. So your algorithm uses some big data structure. This data structure may be very big, and you have to update it. It takes linear space, and but we don't have linear space. So yeah, bad luck. It doesn't work. So we cannot use this. Or maybe not now, but maybe later we will get back to this idea. Then the next algorithm, divide and conquer. So how did divide and conquer work? So you somehow divide the input into two parts. And you can do it by x-axis, but you can also do it arbitrarily. Okay, so this we can do in constant workspace. We can just divide the input into two parts, maybe like this. So this is very easy. And then you solve the problem individually on two halves, and then you combine the solutions. And so again, the question, so does it work in my model or does it not work in my model? No?
Because of stack of recursion.
Exactly. So.
You have to store the convex hulls.
Right. Exactly. There's again two problems. So first of all, the first problem is more obvious, and the second problem is less obvious. And so the first problem, as you mentioned, is you have to store the convex hulls, right? So you have to combine the sub-solutions. And in order to combine the sub-solutions, again, you need to remember what they were, right? So, and you need to store somehow the results of the recursion. And sometimes you can get around this by changing the recursion so that you don't have to store two results but just one, and then maybe it would work. But you have to store two results, you have to combine them, and I don't see how to fix it. And the second problem, which is maybe more subtle, is that you have to have a stack in the recursion. And so even if I could somehow, if I only had a constant size of the problems that, of the results that I get back, not a linear size like here, I still need to store my recursion stack, and the recursion stack, it needs to be stored here in this memory, and I only have a constant amount of memory. And usually, if I do recursion, I need log n. If I'm lucky with some divide and conquer algorithm, but in a typical divide and conquer algorithm, I need log n bits of log n levels in my recursion, and that's too much. right? So that's the second problem. And I mean, that's more subtle, because usually when you count memory, you don't count the stack for the recursion. So this also doesn't work. So now this is depressing, so it seems like nothing works. But we still have a last candidate, which I put down here. And so now gift wrapping, you all know how gift wrapping works. So, right, so you start here. So you have some line. But the idea is somehow you start with a vertical line through the leftmost point, and then you rotate it until you hit the first point. And then this gives you the first edge of the convex hull, and you have some line. And then you rotate it about the other endpoint of this edge until you hit the next point like this, and then this gives you the next edge of the convex hull, and so on, right? And so now the big question is this a constant? Does this work in my model or not? Yes, so this works in my model. And why does it work? So why does it work where all the others do not work? Because the state that you need to remember is, so what do you need to remember for this algorithm to work? You only need to remember this line here. You need to know where's this line. You can forget about all the past. You don't need to remember what happened before. It's not important. You already did this. You output the result. You only need to know where you are right now. And then you can do the next step by like one scan through the input. Then you find the next line. You don't need to do anything fancy. And you get the next line. You don't need to remember. And you'll know when you get back to the leftmost point, you will be done. Right, and that's it. And so you just need to store a constant amount of information. You need to store this line here. Yes, and so this works. So the problem has been solved. So this model, so this is good news, because it says that the model is somehow interesting. At least simple problems can be solved in the model simply, which is good, right? So it says that maybe then more complicated problems can also be solved, maybe not so simply, but then that's what we want, because we want to have some challenge in our lives. But at least something simple works for some simple question, and so this is good. And so at least, so here we know, so how much time do we have? So we need O of n time h time in O of 1 space. So this works because we have a constant amount of space, and the time is n. N is the number of points in the input, and h is, so you may recall that gift wrapping is an output-sensitive algorithm. So h is the number of edges in the hull. Yes, so now we have some good feeling for the next lecture. We solved one problem, and in the next lecture we will solve more problems like this. Right? Okay, yes, so that's all I wanted to say. Yeah, thank you. And so I don't know, do you still want to ask questions, or do you want to have coffee? Or you can also ask questions during coffee. Or you have one pressing question, yes?
What's the lower bound in this model for convex hull?
It's a good question. I would say, output sensitive, I don't know. In the other model, I would think that the sorting lower bound may apply, but I'm not very sure. So, and for sorting, the problem is solved. So I would think that n squared is a lower bound. If you say, because n squared is a lower bound for sorting, this we know. So we know for sorting you cannot do better than n squared. But for convex hulls, it may be that in this model there's a difference, but I'm not so sure. But it's a good question, very good question. Yeah. So yeah, that's it. Yeah, thank you.